Imagine waking up tomorrow morning. You reach for your phone. It's useless. No signal, no data. You try to check the weather. Nothing. You get in your car and the GPS shows a blank screen. You turn on the television. Most channels are down. You try to withdraw cash from an ATM. The network is offline. This isn't a power outage. It's not a cyber attack. It's something far more permanent and far more terrifying. Overnight, a cascading collision in orbit has destroyed thousands of satellites. GPS systems that guide aircraft, ships, and your morning commute, gone. Communication satellites that connect continents, shattered. Weather satellites that predict hurricanes and save lives, obliterated. Military reconnaissance systems that maintain global security, wiped out. In a matter of hours, decades of space infrastructure has been reduced to fragments traveling at 17,000 miles per hour, each piece a bullet capable of destroying anything it hits, creating more fragments, triggering more collisions in an unstoppable chain reaction. This is Kessler syndrome, and it's not science fiction. It's a real, scientifically predicted phenomenon that could make low Earth orbit, the region where most of our vital satellites operate, completely unusable for decades or even centuries. Right now, there are tens of thousands of pieces of space debris orbiting Earth. Every single one is a potential trigger for catastrophe. We're playing Russian roulette with our technological civilization, and most people don't even know the gun exists. Today, we're diving deep into the unseen threat above us, understanding what Kessler syndrome is, how we created this danger, what happens if we fail to address it, and whether we still have time to prevent the catastrophe. Welcome to the fragile frontier. Let's explore the threat that could end the space age before it truly begins. Before we can understand the solution, we need to grasp the problem. What exactly is Kessler syndrome, and why does it pose such an existential threat to our space-dependent civilization? The concept was first proposed in 1978 by NASA scientist Donald Kessler. His insight was simple but profound. At a certain density of objects in orbit, collisions become inevitable. When those collisions occur, they create fragments. Those fragments cause more collisions, creating more fragments. Eventually, you reach a critical threshold where collisions happen faster than debris can naturally deorbit through atmospheric drag. At that point, the process becomes self-sustaining, a runaway cascade of collisions that continues for decades or centuries, regardless of whether we launch anything new. Low Earth orbit becomes a shooting gallery, where operating satellites are progressively destroyed by the debris field we created. Think of it like an avalanche. One rock falls, dislodging others. Those rocks hit more rocks. Within moments, thousands of tons of rock are thundering down the mountain. Kessler syndrome is an avalanche in orbit, except instead of rocks, it's fragments traveling at speeds that make bullets look slow. And instead of stopping at the bottom of a mountain, it continues indefinitely. Why does this matter to you sitting safely on Earth's surface? Because modern civilization is fundamentally dependent on satellites in ways most people never consider. GPS doesn't just guide your car, it synchronizes financial transactions, coordinates shipping and logistics, enables precision agriculture, guides emergency services, and underpins military operations. Without GPS, the global economy would experience disruptions measured in trillions of dollars within days. Communication satellites connect continents. They carry internet traffic, phone calls, television broadcasts, and financial data. They enable remote communities to access services. They allow international coordination during disasters. Lose these satellites, and global communication capacity drops by orders of magnitude. Weather satellites provide the data for every forecast you see. They track hurricanes, predict severe storms, monitor droughts, and provide early warning for natural disasters. They're essential for aviation, shipping, agriculture, and emergency management. Without them, we're flying blind, literally and figuratively. Earth observation satellites monitor climate change, track deforestation, detect wildfires, assess crop health, support disaster response, and provide strategic intelligence. They're tools for scientific research, environmental protection, and national security. All of these capabilities, GPS, communications, weather forecasting, Earth observation, depend on satellites operating in specific orbital regimes, particularly low Earth orbit between 200 and 2,000 kilometers altitude. This is also where debris density is highest and where Kessler syndrome poses the greatest threat. The scenario isn't hypothetical doom. We've already seen warning signs. In 2009, an American commercial satellite called Iridium-33 collided with a defunct Russian military satellite called Cosmos 2251. The impact occurred at over 26,000 miles per hour, completely destroying both satellites and creating over 2,000 trackable fragments, plus countless smaller pieces. In 2021, Russia conducted an anti-satellite missile test, deliberately destroying one of their own defunct satellites. This single act created over 1,500 trackable pieces of debris and countless smaller fragments, forcing astronauts on the International Space Station to shelter in their spacecraft for hours as debris passed nearby. These weren't Kessler syndrome events. The cascade didn't become self-sustaining, but they demonstrated that large collisions create persistent debris fields that threaten other spacecraft for years or decades. Current models suggest we may already be near or past the critical density threshold in some orbital shells. Even if we stopped launching tomorrow, natural collision rates might be sufficient to slowly increase debris density over time. We're not definitively in a runaway cascade yet, but we're uncomfortably close to the edge. The silent threat above us isn't distant or theoretical. It's immediate, growing, and largely invisible to everyone except the small community of space operators who track debris and maneuver satellites to avoid collisions on a weekly basis. How did we get here? How did the pristine environment of space become a junkyard threatening our technological infrastructure? The answer is decades of launches, minimal regulation, and the accumulated consequences of treating orbit as unlimited free real estate. The space age began on October 4, 1957, when the Soviet Union launched Sputnik 1, humanity's first artificial satellite. It was a small sphere, about the size of a beach ball, that orbited Earth for 3 months before atmospheric drag pulled it down to burn up. But Sputnik didn't go to orbit alone. The rocket stage that carried it into space also reached orbit. When Sputnik's mission ended and it burned up, that rocket stage remained. It eventually deorbited too, but for months, humanity's space footprint consisted of both the functional satellite and its defunct launcher, a 2.1 ratio of junk to working spacecraft. That ratio has only gotten worse. Every satellite launched requires a rocket. Historically, upper stages of those rockets often remained in orbit after deploying their payloads. Some missions involved separating satellites from their launch vehicles using explosive bolts, creating fragments. Some satellites experienced battery explosions or propellant leaks years after their missions ended, fragmenting into dozens or hundreds of pieces. The Cold War era saw both superpowers conducting anti-satellite weapon tests, deliberately destroying targets in orbit and creating debris fields. China's 2007 ASAT test destroyed the Fengyun 1C weather satellite, creating over 3,500 trackable fragments, the single worst debris-creating event in history. That debris will remain in orbit for decades. From 1957 to 2000, roughly 5,000 satellites were launched. From 2000 to 2020, another 3,000. Since 2020, the pace has exploded. Companies like SpaceX, OneWeb, and Amazon are deploying mega-constellations, networks of thousands of small satellites providing global internet coverage. SpaceX alone has launched over 5,000 Starlink satellites as of late 2024, with plans for potentially 40,000 or more. These constellations offer genuine benefits: global internet access, including remote and underserved areas, but they also dramatically increase orbital congestion. The types of debris we're dealing with vary enormously. Spent rocket stages are the largest, multi-ton objects tumbling through space. Defunct satellites range from tiny CubeSats weighing kilograms to massive spacecraft weighing tons. Mission-related debris includes lens caps, protective covers, separation mechanisms, and other hardware jettisoned during satellite deployment. Fragmentation debris from explosions and collisions includes everything from meter-sized chunks down to millimeter-scale particles. Even paint flakes, eroded from spacecraft surfaces by radiation and thermal cycling, become hazardous projectiles at orbital velocities. Size matters, but so does velocity. At orbital speeds, around 17,000 miles per hour in low Earth orbit, even tiny objects carry enormous kinetic energy. A 1 centimeter paint flake impacts with the energy of a bowling ball dropped from a skyscraper. A 10 centimeter fragment has the energy of multiple sticks of dynamite. Current tracking capabilities depend on object size. The US Space Surveillance Network tracks approximately 27,000 objects larger than 10 centimeters. Statistical models estimate there are roughly 500,000 pieces between 1 and 10 centimeters, and over 100 million pieces smaller than 1 centimeter. We can track the largest debris and maneuver satellites to avoid it. But we can't track the hundreds of thousands of mid-sized pieces, and we certainly can't track millions of small fragments. These create an invisible minefield that spacecraft pass through, hoping statistical odds remain in their favor. As of October 2025, the situation continues deteriorating. Launch rates are at all-time highs. Mega constellations are expanding. Debris from past collisions and explosions remains in orbit. And critically, we're launching faster than old debris is naturally deorbiting. Low Earth orbit has a natural cleanup mechanism, atmospheric drag. At lower altitudes, the tenuous outer atmosphere gradually slows satellites until they deorbit and burn up. But this process takes time. Debris at 400 kilometers altitude might deorbit in months to a few years. At 600 kilometers, it could take decades. Above 1,000 kilometers, debris can remain in orbit for centuries. This means that every piece of debris created today is a problem for decades or centuries. We're not just managing current congestion, we're inheriting the accumulated mistakes of 67 years of spaceflight. The clutter problem is compounded by economics. Satellites are expensive, often hundreds of millions of dollars for large spacecraft. When a satellite reaches end of life, operators face a choice: spend fuel and time deorbiting it properly, or leave it in orbit and use remaining resources for the next mission. Historically, many chose the latter. International guidelines now recommend deorbiting within 25 years of mission end. But compliance is inconsistent, and enforcement is essentially non-existent. We've treated orbit as infinite and consequence-free. We launched without planning for disposal. We tested weapons without considering the debris. We operated under the assumption that space is big enough to absorb our waste. That assumption was wrong, and we're now facing the consequences of a century of clutter. Let's walk through what actually happens during a Kessler syndrome cascade, why it's so devastating, and what the consequences would be for life on Earth. Picture a 1-ton defunct satellite tumbling through orbit at 17,500 miles per hour. It's been dead for years. No power, no propulsion, no way to maneuver. Also in orbit is a 10-centimeter fragment from a previous collision, traveling in a slightly different orbit at a similar velocity. Because they're in different orbital planes, their relative velocity at impact is much higher than either object's individual speed, potentially 30,000 miles per hour or more. When they collide, the kinetic energy is astronomical. The impact is instantaneous and catastrophic. The fragment punches through the satellite's structure. Metal vaporizes from the impact energy. The satellite's structure buckles and fragments. If it has residual fuel or charged batteries, those explode. Within milliseconds, what was one large object and one small fragment has become hundreds or thousands of pieces, each traveling at high velocity in slightly different orbits. These fragments spread out over hours and days, forming a debris cloud in roughly the same orbital altitude. Each fragment is now a projectile capable of destroying anything it hits. Days or weeks later, one of these fragments encounters another satellite, perhaps a functioning communications satellite providing internet and phone service to a remote region. The impact destroys that satellite, creating another cloud of fragments. Those fragments spread, and some collide with other objects, more satellites, spent rocket stages, existing debris. Each collision creates more fragments. The population of debris doesn't grow linearly, it grows exponentially. One collision creates 100 fragments. Those cause 10 more collisions, creating 1,000 fragments. Those cause 100 collisions, creating 10,000 fragments. The cascade is self-sustaining. Even if humans stopped launching entirely, the collision rate would continue increasing as debris density rises. The process could take decades to fully develop, but once started, it's essentially unstoppable with current technology. Which satellites are most at risk? Essentially, all of them in the affected orbital shells, but critical infrastructure faces the greatest impact. GPS satellites orbit at approximately 20,000 kilometers, higher than most debris, but ground stations, signal processing, and some augmentation satellites operate in lower orbits. Losing those support systems degrades GPS accuracy and availability. Communication satellites span various altitudes. Low Earth orbit constellations like Starlink, OneWeb, and future Amazon Kuiper satellites operate between 500 to 200 kilometers, right in the debris danger zone. Geostationary satellites at 36,000 kilometers are safer from LEO debris, but face their own congestion challenges. Weather satellites primarily orbit between 700 to 900 kilometers, again squarely in the danger zone. Most Earth observation and reconnaissance satellites operate at similar altitudes, optimizing for image resolution and revisit times. The International Space Station orbits at approximately 400 kilometers. Debris from collisions at higher altitudes would eventually deorbit past the ISS's orbital altitude, creating ongoing hazards for crewed missions. Now let's discuss consequences. Start with economics. There are approximately 7,000 active satellites in orbit as of late 2024. Replacing them would cost conservatively $500 billion to over $1 trillion, depending on satellite types and launch costs. But you can't just rebuild them. Orbit is unusable. The replacement satellites would be destroyed by debris within months or years. The global space economy is valued at approximately $500 billion annually and growing rapidly. A Kessler cascade would devastate this sector. Companies dependent on satellite services, telecommunications, media, logistics, agriculture, defense would face massive disruptions. GPS disruption alone would cost the US economy an estimated $1 billion per day, according to some analyses. Global impacts would be multiples of that. Financial systems rely on GPS for time synchronization. Shipping and logistics depend on it for tracking and routing. Precision agriculture uses it for planting and harvesting. Emergency services need it for dispatch and navigation. Weather forecasting without satellites would regress to 1960s capability, essentially ground observations and limited aircraft data. Hurricane tracks would be uncertain until storms approached coasts. Severe weather warnings would be delayed. Aviation and shipping would operate with dramatically reduced situational awareness. Global communication would be severely degraded. While fiber optic cables carry most internet traffic, satellites handle remote connectivity, maritime and aviation communication, media distribution, and backup capacity. Losing satellite capacity would create bottlenecks and eliminate service to millions in remote areas. Military and intelligence capabilities would be compromised. Reconnaissance satellites provide strategic warning, monitor potential threats, verify arms control treaties, and support tactical operations. GPS guides precision weapons. Communication satellites enable global command and control. Losing these capabilities would fundamentally alter military balance and increase geopolitical instability. The societal impact extends beyond economics. Confidence in technology would be shaken. Trust in government and institutions would erode if they failed to prevent a predictable catastrophe. Remote communities dependent on satellite connectivity would be isolated. Developing nations relying on satellite services for leapfrog development would be set back decades. Perhaps most concerning is the long-term implication. Low Earth orbit could become unusable for decades or centuries. Every piece of debris eventually deorbits, but the process is slow. At 800 kilometers altitude, debris can remain in orbit for decades. Above 1,000 kilometers, centuries. During that time, launching new satellites would be suicidal. They'd be destroyed almost immediately. This means humanity could be effectively locked out of low Earth orbit for generations. Space exploration would be stalled. Scientific research from orbit would cease. The benefits we've come to rely on, GPS, weather forecasting, global communication, would be degraded or lost. Kessler syndrome isn't an extinction event. Life on Earth continues, but it would be a civilizational setback, erasing decades of technological progress and foreclosing opportunities for space development that could benefit billions of people. The domino effect isn't just about satellites colliding, it's about the cascading consequences rippling through every aspect of modern life that depends on technology we've come to take for granted. The picture we've painted is dire, but we're not helpless. Multiple strategies exist to mitigate debris creation and potentially reverse the accumulation. The question is whether we'll implement them quickly and comprehensively enough. Let's start with prevention, stopping the problem from getting worse. The most straightforward approach is proper end-of-life disposal. When satellites reach the end of their missions, they should be moved to disposal orbits or actively deorbited into Earth's atmosphere to burn up. For satellites below 600 kilometers, atmospheric drag naturally brings them down within 25 years, the internationally recommended disposal timeline. But this requires leaving enough fuel and power to perform deorbit maneuvers. Many satellites historically haven't reserved those resources. Above 600 kilometers, natural deorbit takes decades or centuries. These satellites should be moved to higher graveyard orbits above the useful zone or actively deorbited using propulsion systems. But again, this requires planning and resources. New satellite designs increasingly incorporate deorbit mechanisms. Drag sails deploy at end of life, increasing atmospheric drag to accelerate natural deorbit. Electrodynamic tethers interact with Earth's magnetic field to produce drag. Chemical or electric propulsion systems can perform controlled re-entry burns. SpaceX's Starlink satellites, for example, are designed to autonomously deorbit at end of life, burning up completely in the atmosphere. This is responsible design, though it remains to be seen how reliably these systems work across thousands of satellites over decades. Passivation, rendering defunct satellites inert, prevents explosions that create debris. This means venting propellant, discharging batteries, and ensuring no stored energy can trigger fragmentation years after the mission ends. International guidelines recommend passivation, but compliance varies. Launch vehicle stages present challenges. Historically, many upper stages remained in orbit after payload deployment. Modern best practices call for controlled re-entry or moving stages to disposal orbits. Some rockets now include restartable engines specifically to enable disposal maneuvers. Collision avoidance is critical for operating satellites. Organizations like the US Space Force's 18th Space Defense Squadron track debris and provide conjunction warnings, notifications when objects are predicted to pass dangerously close. Satellite operators can maneuver to avoid predicted collisions if warnings are timely and accurate. But avoidance only works for tracked debris. The hundreds of thousands of untracked fragments create unavoidable risk. Every satellite faces statistical odds of catastrophic impact that increase as debris density grows. This brings us to active debris removal, actually going to orbit and cleaning up existing debris. This is technically challenging and expensive, but potentially necessary to prevent cascade scenarios in critical orbital shells. Several concepts are under development. Harpoons or nets can capture defunct satellites or large debris pieces. Robotic arms can grapple objects for controlled deorbit. Lasers, either ground-based or space-based, can ablate material from debris surfaces, creating thrust that alters orbits and accelerates deorbit. Electrodynamic tethers deployed from service spacecraft can deorbit multiple debris objects. Shepherding spacecraft can rendezvous with debris, attach propulsion modules, and guide them to re-entry. The European Space Agency's Clear Space 1 mission, planned for the mid-2020s, aims to demonstrate active debris removal by capturing and deorbiting a defunct rocket upper stage. Other missions from Japan, Russia, and commercial entities are in development. But the economics are daunting. Removing one piece of debris costs tens of millions of dollars. There are tens of thousands of trackable objects and hundreds of thousands of dangerous fragments. Comprehensive cleanup would cost trillions. And new debris is created faster than we could possibly remove it with current technology. This means active debris removal can't solve the problem alone. At best, it can remove specific high-risk objects, large defunct satellites in critical orbits, that pose the greatest collision risk. It's triage, not cure. Just-in-time collision avoidance is another concept. Instead of removing debris years in advance, detect imminent collisions and perform last-second maneuvers to prevent them. This requires rapid detection, prediction, and response capabilities that don't currently exist at necessary scales. International cooperation is essential, but frustratingly inadequate. Space is global commons. Debris created by one nation threatens everyone's satellites. But space regulation is fragmented. The United Nations has guidelines for debris mitigation, but they're voluntary. The Interagency Space Debris Coordination Committee develops technical standards, but compliance is inconsistent. National regulations vary widely in stringency and enforcement. Some experts advocate for binding international treaties with mandatory debris mitigation requirements, cleanup obligations, and potentially fees or liability for debris creation. But achieving consensus among spacefaring nations, particularly amid geopolitical tensions, is extremely difficult. The Outer Space Treaty of 1967 establishes that nations are liable for damage caused by their space objects, but enforcing this for debris is complex. If a Chinese rocket stage fragments and a piece destroys an American satellite years later, determining liability and securing compensation is legally murky. There's also the fundamental prisoner's dilemma. Every nation benefits from others cleaning up debris, but each nation bears the full cost of their own cleanup efforts. This creates incentives to free ride, letting others bear cleanup costs while you continue launching. Breaking this deadlock requires either enlightened self-interest, recognizing that everyone loses if debris cascades make orbit unusable, or enforcement mechanisms that don't currently exist. Time is critically important. Current models suggest we may have a decade or two before debris density in key orbital shells makes cascades likely. Implementing solutions requires years of technology development, testing, and deployment. The window for action is closing. We're not without options. Technology exists or is being developed to address the threat. But translating that technology into deployed operational systems at the scale needed requires political will, international cooperation, and substantial financial investment that, so far, has been insufficient. Let's step back and consider the broader implications. What does the Kessler syndrome threat tell us about humanity's relationship with space, and what's at stake for our long-term future? The immediate concern is protecting current capabilities, but there's a longer view. If we fail to address space debris, we may foreclose humanity's future in space entirely, at least for generations. Low Earth orbit is the gateway to everything beyond. It's where we assemble spacecraft for deeper missions. It's where we conduct microgravity research, Earth observation, and technology development. It's the training ground for human spaceflight and the economically accessible region for commercial space activities. If LEO becomes impassable due to debris, we're locked on Earth. Not permanently. Debris eventually deorbits, but for decades or centuries. During that time, opportunities are lost. Consider space-based solar power, collecting solar energy in orbit where the sun always shines and beaming it to Earth. This could provide clean, abundant energy, addressing climate change and energy poverty, but it requires infrastructure in orbit, including satellites in LEO for construction, testing, and operation. Space manufacturing could produce materials and products impossible to make in Earth's gravity. Pharmaceuticals, fiber optics, alloys, and more could be manufactured in orbit and returned to Earth, creating new industries. Again, this requires reliable access to LEO. Space tourism and eventually space settlement require routine, safe access to orbit. If debris makes launch windows narrow and risky, commercial space activities become economically unviable. Scientific research from orbit has transformed our understanding of Earth, the cosmos, and fundamental physics. Astronomy benefits from space telescopes above atmospheric distortion. Earth science relies on satellite observations. Human spaceflight has yielded insights in biology, medicine, and materials science. Debris-induced limitations would constrain research for generations. There's also the inspirational aspect. For thousands of years, humans looked up at stars and dreamed of reaching them. In 1969, we walked on the moon. That achievement inspired generations to pursue science, engineering, and exploration. We told children they could reach for the stars. What message do we send if we trash the orbital environment so badly that we lock ourselves out of space? That humanity's reach exceeded our responsibility. That short-term convenience trumped long-term vision. Kessler syndrome is, in many ways, a test case for humanity's ability to manage global commons responsibly. We've seen similar challenges with overfishing oceans, deforestation, climate change, and other tragedies of the commons, where individual incentives conflict with collective welfare. Space debris is unique because the consequences are immediate, the solution window is limited, and the problem is entirely self-inflicted. We created every piece of debris in orbit. No natural phenomenon caused this. We can't blame outside forces. This is on us. Solving it requires transcending national interests and short-term thinking. It requires viewing orbit as shared heritage that we're obligated to preserve for future generations. It requires investment in solutions that may not provide immediate returns, but prevent catastrophe. These are precisely the capabilities humanity struggles with. We're evolved for immediate threats we can see and touch. A predator charging requires instant response, and we're built for that. Slow-building invisible threats that require coordinated, sustained response across cultures and generations. We're terrible at those. Climate change is the obvious parallel. Decades of warnings, clear scientific consensus, enormous potential consequences. Yet meaningful action is slow and contentious because costs are immediate and concentrated, while benefits are diffuse and distant. Kessler syndrome has one advantage. The consequences aren't distant. A cascade could begin within years. If it does, impacts would be immediately obvious to everyone relying on GPS, weather forecasts, or satellite communications. This immediacy could drive action that slower developing threats don't generate, but it also means we have less time. We can't afford decades of debate and incremental progress. The problem demands urgent, comprehensive response. There's also economic opportunity in the challenge. Space debris removal, satellite servicing, orbit management, and related technologies represent new industries worth potentially billions of dollars. Companies developing these capabilities could capture significant markets while solving a critical problem. Some space companies are treating debris seriously. SpaceX designs for deorbit. Astroscale is developing removal technologies. Northrop Grumman has demonstrated satellite servicing. These efforts are encouraging but need to scale dramatically. Individual awareness matters too. Most people never think about space debris. It's invisible, abstract, technical. But the services people use every day depend on satellites threatened by debris. Public pressure can influence policy. When citizens understand that GPS navigation, weather forecasts, and communication services are threatened, they can demand action from governments and companies. Environmental movements succeeded partly by making invisible problems visible and personal. We need a similar shift in consciousness about orbital environment. Space isn't infinite. Orbit isn't free. Debris is everyone's problem, and we have both the responsibility and capacity to address it. The fragile frontier above us is worth protecting, not just for our benefit, but for generations who will inherit our decisions. We can be the generation that recognized the threat and acted, or the generation that watched the cascade begin. We opened this video with a nightmare scenario. Waking up to find GPS, weather forecasts, and global communication systems disrupted by a cascade of space debris collisions, Kessler syndrome manifesting into catastrophic reality. This isn't inevitable, but it's possible, increasingly probable if we don't act, and potentially imminent if current trajectories continue. We've traced how a century of spaceflight created an orbital junkyard. We've examined how collisions cascade exponentially, destroying infrastructure and denying access to space for generations. We've explored solutions, deorbiting, tracking, active removal, international cooperation, and their limitations. The fundamental challenge is this. Space debris is a tragedy of the commons playing out in real time. Every launch benefits the nation or company conducting it. The debris created is everyone's problem. Individual incentives favor continued launching and minimal cleanup. Collective welfare demands restraint and expensive remediation. Breaking this dynamic requires shifting from competition to cooperation, from short-term gain to long-term stewardship, from treating orbit as infinite to recognizing it as finite and fragile. Is this achievable? History offers mixed lessons. We've sometimes managed global commons successfully. The Montreal Protocol addressed ozone depletion through international cooperation. More often, we've failed until crises forced action. The question is whether we're wise enough to act before the crisis rather than after. Because with Kessler syndrome, waiting until cascades begin means waiting too long. Once collisions become self-sustaining, solutions become exponentially harder or impossible with current technology. We still have a window, narrow and closing, but open. We have technology to mitigate debris creation and remove the highest risk objects. We have international forums to coordinate action. We have growing awareness among experts, policymakers, and the public. What we need is urgency commensurate with the threat, investment sufficient to implement solutions at scale, and sustained commitment across years and decades to reverse the accumulation we've created. For everyone watching, the message is simple. Space debris isn't someone else's problem. It threatens services you use daily. It endangers humanity's future in space, and solving it requires collective pressure on governments and companies to prioritize orbital sustainability over short-term convenience. Ask your representatives about space debris policy. Support companies implementing responsible practices. Demand transparency about debris creation and removal. Make this invisible threat visible through your awareness and advocacy. The unseen threat above us won't remain unseen forever. Either we address it proactively, preserving orbit for future generations, or we wait until the cascade begins and learn the hard way that space isn't infinite. Our children and their children will judge us by the orbital environment we leave them. We can be remembered as the generation that recognized the threat and acted, preserving humanity's access to space. Or we can be the generation that watched the problem grow and did nothing, foreclosing possibilities for countless future generations. The choice is ours. The window is now, and the clock is ticking. Thank you for exploring this critical but often overlooked threat with me. Look up tonight. That starfield contains tens of thousands of pieces of debris we've created. Whether it remains navigable or becomes impassable depends on decisions we make today. The frontier is fragile, but it's not yet lost. Let's ensure it never is.